Welcome back, everybody. So we are in the second part of the 11.1 notes here. So part 3, or question 3 here is just going to ask us to sketch the parametric equations. And then we want to indicate the direction of the trace. So this will be similar to what we worked on the first part. So we'll note in the first one here, part A, our coefficients are the same, and we've chosen sine and cosine. So this is going to be some representation of the circle with radius 3. So this is going to be x squared plus y squared equals 9. But even if we don't know that, we can still sketch the trace just by using the given values. So we can choose nice values between 0 and 2 pi. And then compute. So we'll have 3, 0. So this is cosine and sine. So this is going to be when we calculate our typical representation of the circle. So we'll start at standard position. And our trace is going to be counterclockwise. And we get one complete trace. Now for B, now we've got different coefficients. So this is obviously going to look a little bit different here, but we're still doing sine and cosine between 0 and 2 pi, so we can still choose nice values at the axes. All right, so let's see what we get here. So 0, we're going to have 0, 3. And I think you might be able to guess what our answers are going to look like here. Pi over 2 is going to be 5, and 0 pi is going to be negative 3, 0, negative 3. 3 pi over 2 is going to be negative 5, 0. And then we'll be back at 0, 3. So we can see here that we're going to start at 0, 3. So we're going to start at the y-axis, and then we're going to rotate to the x-axis, back to the y, back to the x, and we're going to end up with an ellipse that is 5 by 3. And our trace is going to be clockwise. So if we have sine and cosine with mismatched coefficients, then clearly it's going to be some kind of ellipse. So it's going to be a slightly warped graph, which in this case would just be x squared over 25 plus y squared over 9 is equal to 1, obviously. All right. Number 4 is going to be our introduction to the cycloid, which is a really cool object. If you look in your textbook, there are some good explanations of the cycloid, so you can look up that derivation of the cycloid in the textbook in section 11.1. In general, the equation is going to look like this. Sometimes instead of t, they'll use theta. So note t is variable, r is a constant. And r is going to determine, how large your rolling cycloid is going to be. So again, the cycloid here is going to be the path traced by this circle as it rotates. So if we were to take this circle here and fix this point at the bottom and follow that point as it rotated, one complete rotation, that round sort of circular shape that you end up with is the cycloid itself. The curve is the cycloid, which, looks like a semicircle, but it's not quite a semicircle. So this is a very famous curve used to solve a number of early calculus problems involving chains and paths followed by objects in space. And so for this, on your graphing calculators or on Desmos, you can graph what those look like with r is equal to 1, 2, and 3. So see how r changes the shape of the graph. And then also you can extend the domain so that you get multiple cycloids. So it's going to repeat over and over again, which is kind of cool. So you don't need to memorize these equations. So I'm not going to ask you to like derive this cycloid or anything like that, but you might be given some problems with that cycloid. And so this will be good to at least have seen it here before working on those examples. All right, so then the remaining examples are going to be to eliminate the parameter and find the rectangular equation if possible. So it might not be possible, so we'll have to see here. So some of these can get quite messy. So we've got some exponential parametrics here, as well as some other types. So let's go ahead and just get started. So again, our goal is going to be to solve for t. Use a slightly smaller font here. So we know that x minus 1 is equal to e to the t. So then in order to solve for t, I need to use the natural logarithm. So natural log of x minus 1 is going to equal t. And now we can sub that in for y. So we'll sub that into our y equation. So we'll get y is equal to e to the 3 natural log of x minus 1 plus 2. And then we can write this as e to the natural log of x minus 1 cubed plus 2, which is just going to be x minus 1 cubed plus 2. So we'll just note that our actual rectangular equation here is just a cubic. All right, for B, we could, again, solve for t, but what we can notice here actually is that y is just 2t. So it might be easier in this case just to solve for t in terms of y and sub in the opposite direction. So what we'll end up with is x is equal to 3 times 1/2 of y squared minus 4, which is going to end up being x equals 3/4 y squared minus 4. So now it's going to be a function of y instead of a function of x, but that's perfectly fine. So it's still a rectangular equation. And note in these examples, we're not given specific domains also. So C, we're given a specific domain, but the other ones we're not. So we won't make any assumptions about what type of curve this should be. For C, so what are we going to get for C? Okay. So we know t is greater than 0, so that's good to know. But we've got a quadratic and then an exponential. So this is going to be quite messy, it looks like. So let's think about how we can solve this. So we need to isolate t. So we've got this quadratic, and then we've got this exponential. So it looks like I'm going to have to start with the x equation. And in order to isolate t, however, I need to somehow make this into some sort of a linear expression, either squared or completed. So what I'm going to want to do is complete the square. So we'll just note off to the side here, t squared plus t plus 1/4. So half of the middle term squared would equal t plus 1/2 squared. So that's what we want. And we'll note we got a -1 here, so that's not going to help us. So we're just going to have to add 1/4 to both sides. So let's go ahead and do that. So we'll have x plus 1/4. Or actually, yeah, x plus 1/4, and then we'll have t squared plus t plus 1/4 minus 1. So again, we'll add that 1/4 to both sides. I can add the 1 over to the right-hand side, to the left-hand side actually also. So we'll just get x plus 5/4. And then we'll have t plus 1/2 squared. And now we can square root. So we're going to have x plus 5/4. is equal to t plus a half. And because t is positive, we're going to have a positive square root, so we don't need to worry about plus or minus here. And so then we'll end up with t equaling rad x plus 5/4 minus a half. And then we just plug all that into our y function, so, or y expression. So we'll have rad x plus 5/4 minus a half. And then e times 2 rad x plus 5/4 minus a half times t. And so you can clearly see here, right, that this is going to be a mess, right? So the rectangular equation here is pretty brutal, but the parametrics are much nicer. So the parametrics here are really, really nice compared with this ugly expression below. All right, and let's see here. All right, so now we've got some trig expressions. So we can see there's a cosine squared here, a cosine here. So we definitely probably want to try to substitute that expression in terms of x. So let's solve for cosine of 2t. So x over 3 is equal to cosine of 2t, which we can then plug in, and we'll get y is equal to 1 plus x over 3, quantity squared. So 1 plus x squared over 9. Yeah, so eliminating the variable is going to be something that we need to do from time to time, so getting a little bit more practice in with that is going to be good. All right, oops. So then continuing on, that's the end. So this is going to be just kind of our introduction. The homework will, again, have you sketching a lot of these graphs, etc. And so what we'll focus on for the next part is going to be actually computing derivatives with these expressions and looking at some applications where we describe displacement and distance, etc. So if you have any questions, shoot me an email or come by the office hours.